Okay everyone, I'm going to do another couple examples with synthetic division and finding the zeros of polynomials. So we're going to perform this synthetic division dividing x to the fourth minus 256 by x minus 4, and we're going to write the result in both forms that we're seeing listed here. Alright, so the first one where we're actually writing out the division, and the second one from the division algorithm listed there. Alright, so let's get started with that. I've got this laid out a little bit. Just a reminder, with the numerator, with the dividend polynomial, if there are some x terms missing, we want to put them in descending order and include those coefficients. So we've got zeros for the coefficients for the x cubed, squared, and x terms. Alright, so with a synthetic division, we bring down the 1, right? We're going to be eventually adding here. So what we always do is multiply with the number 4. Again, where does the number 4 come from, right? It comes from the x minus whatever that value is. So that 4 is lining up with our 4 in the box there. I'm just going to take that highlighting off now. Alright, so we bring the 4 down. We multiply 4 by 1 to get 4. Alright, add that result. 0 plus 4 is 4. Do it again. 4 times 4 is 16. Add that result. 0 plus 16 is 16. 4 times 16 is 64. 0 plus 64 is 64. And then lastly, 64 times 4 is positive 256. Turns out we get a remainder of 0 here. All right. Now, the key thing to know for synthetic division is we're dividing. The only time we can use synthetic division is when we're dividing by x minus a number. In our case, we're doing x minus 4. Or if it's x plus a number, then we're going to write that as x minus the opposite of that number. And the second thing is, this number is always going to be your remainder. In this case, it came out to be 0, which means that's going to be a factor of our polynomial. These are the coefficients of the quotient polynomial. All right, and in terms of the division algorithm, we write that as q of x. All right, so up here, up above here, we've got q of x. That's standing for our quotient polynomial. Since we're dividing by a polynomial of degree 1, x minus 4, our remainder has to be a polynomial of smaller degree. Less than degree 1 would mean degree 0, which means it has to be a number. So that's why we have numbers here as little r, not r of x. Those got to be numbers there. All right, now let's write that out. What does that mean in terms of this? Let's write it in these two different forms before we do some other things with polynomials. So that would say to us then x minus 4 over 256 divided by x to the fourth, minus 256 divided by x minus 4 would equal our quotient polynomial, and that has 4 terms, okay? And if it has 4 terms, there's a constant term, an x term, a square term, and then a cubic term. So the first one's going to be 1x cubed plus, I'm putting the 1 in there for emphasis, 4x squared plus 16x plus 64. All right, and then that's going to be times our, we're going to add on then our remainder divided by our divisor polynomial. Now, in our case, we would get 0 divided by x minus 4. All right, so not necessary to write that down. It divides in evenly. All right, writing it the other way would say that our dividend polynomial, x to the fourth minus 256, would equal x minus 4 times our quotient polynomial, which again is just going to be 1x to the third power plus 4x squared plus 16x plus 64. All right, and again, it would be plus 0. Not necessary to write that whatsoever. So again, writing the plus 0 doesn't add anything on to us here. All right, so I'm just going to erase the plus 0 parts from this. All right, we don't need those on there. They're gone. All right, so again, that's synthetic division. Just wanted to go through that example to emphasize that we need to include zeros sometimes for these problems. Okay, moving on. I want to talk just a little bit about the remainder theorem and how that implies the factor theorem. So what this is saying is if you take the function f of x, the polynomial function, if you divide it by x minus a number, then you're going to end up with your quotient polynomial plus the remainder divided by x minus k. All right, what this is saying is that remainder, little r, has to be f of k. It has to be the function of value at k. Now, that implies the factor theorem, which is important for working with polynomials. All right, and I've started to write some of this. I'm going to continue to put it in here now. What's our conclusion? I'm just going to write that in a different color. If x equals k is a 0, then what does that mean? Well, that means f of k has got to equal 0. When you plug the number k in, you get 0. But from our remainder theorem, it's going to say that f of x then has to equal x minus k, your divisor, times your quotient. But if your remainder is f of k and that's 0, it's plus 0. So we're not going to bother writing that. What does that imply? That implies that x minus k is a factor of the polynomial f of x. Okay, vice versa. If x minus k is a factor, that means we can rewrite the function f of x as x minus k, that number k, times the quotient polynomial. No remainder after that. Well, it's pretty obvious here. If we plug in k for x, we're going to have k minus k times the quotient polynomial evaluated at k, which is going to give us 0 times the quotient polynomial evaluated at k, which is just 0. All right, which tells us that number k is a 0 of that polynomial. All right, that implies what we just showed right there. That's kind of a derivation or a proof of the factor theorem. If you have a polynomial function f of x, then the number k is a 0 if and only if x minus k is a factor. Okay, so that's an important result. We're going to use that combined with the rational zeros theorem to find zeros of certain polynomial functions. All right, so we're going to move on to that now. All right, the rational zeros theorem. All right, let's highlight what's important about it. First thing, we're talking about polynomials. We're writing it in descending order in there, but they're stating it with integer coefficients. You can use this with rational coefficients, all right, but you might have to factor out a certain, like if any of those were fractions, any of these coefficients were fractions, you would have to factor out the an appropriate fraction to make them all integers for this to be applicable. That's doable. It's not going to show up in any of the examples I'm going to go through. But it says every rational zero has the form, so a rational zero means a fractional zero, a rational number, has the form of some rational number, p over q. The number in the numerator, p, is a factor of the constant term, and the number q is a factor of the leading coefficient. All right, so that tells us we really got to key in on these two numbers and look at the factors of the constant term divided by the factors of the leading coefficient. That's going to help us find rational zeros if they exist. This is important because irrational numbers are hard to write down, so polynomials with irrational coefficients are hard to plot. All right, by hand, if you needed to plot it by hand for some reason. All right, some of this math we're going to be doing here is a little bit historical. All right, but it's stuff that we need to cover. So let's look at the steps for finding rational zeros, and then maybe using that to help us graph polynomials, all right, of degree 3 or larger with integer or possibly rational coefficients. Again, we're mostly going to focus on integer coefficients. The first thing we want to do, here's the steps. We want to list off the possible rational zeros. Then we're going to test the candidates. All right, find a rational zero, find one, and then we're going to use synthetic division after that, or polynomial long division. To speed that up, we'll use a graphing calculator or use Desmos to maybe shorten down our list. Again, Desmos can do this quicker than we can do this, but if we need to do it by hand and we don't have access to it, maybe you're taking an exam and you don't have access to Desmos, then you need to know how to, a different approach for this. So again, after you know one of the zeros or find one, we'll use polynomial or synthetic division to help us break that polynomial down, as we showed in the previous example, and factor it as your quotient times your divisor. Keep repeating that process. Sometimes we might have to do that in step 3. You might have to do that more than once. Okay, so you're going to want to repeat the process until you get down to a quotient that's degree 2 or less, and then you can set that equal to 0 to find the rest of the zeros. All right, and if you know, step 5, if you're graphing, use the zeros and make a sign diagram to help you sketch the graph of the polynomial. Okay, I've got an example that we're going to work through here. First off, getting practice listing the possible rational zeros. The coefficient of x cubed is 1. Our constant term is -6. the factors of negative 6 would be 1, 2, 3, and 6. Those are the only numbers that are factors of 6. So listing off the possibilities, including positives and negatives, we would have ratios of 1 divided by 1, 2 divided by 1, 3 divided by 1, 6 divided by 1. Again, the 1's in the denominator is because the leading coefficient for this example is 1. So that makes it quite simple. It's just plus or minus 1, plus or minus 2, plus or minus 3, and 6. All right, now to make this a little bit faster, I've got just a quick picture of the graph here. And looking at the graph, it seems pretty clear from the graphing calculator that x equals 1 looks like a good choice. Or not 1, pardon me, negative 1 looks like a 0. So let's try that. So let's use synthetic division with negative 1. All right, so the way I write this out is I put the negative 1 kind of up in the box. We're going to write our coefficients down, 1, 2, including the signs, negative 5 and negative 6. And then we're going to go through the synthetic division process. Again, this is equivalent to long division. You can do it with long division also. So bring the 1 down. Multiply the number in the box, the negative 1 times 1 to get negative 1. Then add. We get 1. Do it again. Multiply the number in the box by now 1 this time. And we're going to get negative 1 again. Add those together. That gives us negative 6. Watch the signs here. Negative 1 times negative 6 is going to give us positive 6. Adding those together gives us 0. Okay, so for that, we now have shown that yes, negative 1, looking at the graph, seems pretty clear. We just verified it. That x equals negative 1 is a 0. All right, if x equals negative 1 is a 0, then x minus negative 1, which is x plus 1, is a factor of the polynomial. Again, these numbers here that I'm just going to highlight, and then we're going to write it out, those are the coefficients of the resulting quotient polynomial. All right, so when we go to write this out here, we want to express f of x. We want to express the function f of x, which is x cubed plus 2x squared minus 5x minus 6. We are going to rewrite this as x minus negative 1, or more simply x plus 1, times the resulting quadratic polynomial x squared plus x minus 6. All right, so we did the synthetic division. We found that. All right, now if we want to find the remaining zeros, we would set that equal to 0 and solve. For the purposes of this video, I am just going to factor the resulting polynomial, and then we can just list off what the zeros are. What numbers multiply to negative 6 and add up to positive 1? It's x plus 3. Plus 3, yep. Sorry, zoomed out a little bit. It's plus 3 and minus 2. Said it. I didn't write it correctly. So it's x plus 3 and x minus 2. And if we look at that, that's the factored form. So if we want to know what the zeros of this for this polynomial are, they would be setting each factor equals 0 and then solving. I'm skipping that here. We would get negative 1. We already knew that. We would also get negative 3, and we would get positive 2. All right, and that does line up with what we're seeing in that screenshot of the graphing calculator. Okay, I'm going to do a couple more examples in another video.